All right.
2x plus 4 plus 2.
Yep.
2 cosine x for the third.
Yeah. So try the three problems that are on the board. Make sure you're using the rules that are stated next to them. So the first one's the power rule. Second two are the second and third ones are the product rules. There are multiple ways to do these. Yes, I want you to do it specifically that way because I want you to see something.
Is this 2 sine x cosine x?
Yes. No, remember the derivative side is positive. You actually had it right.
I see it.
So the ones that are just coming in, try the three problems on the board. Let me give you guys a couple more minutes before I show the answers. All right. So the first one, using the power rule, derivative of 2x or x squared is 2x. Derivative of 4x is 4. So you should get 2x plus 4 for the first one. The second one, using the product rule, you'd have had x plus 2 times x plus 2. The derivative of x plus 2 is 1. So you have 1 times x plus 2 plus 1 times x plus 2, which again gives you 2x plus 4. If you had FOILed out x plus 2, you'd have gotten x squared plus 4x plus 4. So those two are exactly the same. They were just done two different ways. And actually, I'm going to show you a third way today. Sine squared x, same concept. We would do sine x times sine x. The derivative of sine x is cosine x. So we have cosine x times sine x plus cosine x times sine x, which equals 2 cosine x. We're going to look at another way to do that problem in a minute, actually. So you can see how, depending on the type of problem, like this one, Honestly, it probably would have been just as easy to distribute it out and just use the power rule for it than trying to do the product rule for it. But a problem like sine squared x, you can't just distribute it out. So we had to break it up. There's another way that we're going to look today, what's known as called the chain rule. The chain rule allows us to do things that are functions inside of other functions. So like the x plus 2 squared, that's a function inside of the squared. Or sine x squared, that's a function inside of it. So the quotient or the chain rule. So the chain rule basically states you take the derivative of the function on the inside, and then you're multiplying it by the derivative of the function if the inside didn't exist. So let's look at the problem that we just did a minute ago. Was x plus 2 squared. So the derivative using the chain rule, what's the derivative of the inside? What's the derivative of x plus 2?
1.
1. So it's 1. Now, we're going to look at this like the inside was just a single letter. So if I wrote that as m squared, what's the derivative of m squared? 2m. So I would write this as 2x plus 2, which is 2x plus 4, which is what we got before. So you take the derivative of the inside and then multiply it by the derivative of that inside piece wasn't there. It sounds crazy. It sounds weird. I admit it. But basically what this is showing is it's the g of x. So if you remember back in pre-calculus, you learned composite functions where you're putting functions together. And one of the things or one of the topics that you should have done was also looking at how to split up functions and make them into composite functions. So you had a problem where it was like, say, the square root of x plus 3. That was m of x. And they wanted you to split it up into f of x and g of x so that it was f composed of g. So you would have done the square root of x and x plus 3. Vaguely remember that or no? Huh? Right. You did this and you wanted to get back to that. So, which is fine. The funny part about it is, which a lot of people don't actually do that topic is splitting it apart is actually more important for calculus than putting it together because of the chain rule and U substitution when we start to look at integration. Because what we've got is we've got this function, the square root of x plus 3, and we need to split it apart into those two pieces to be able to do the actual derivative of it. Because we don't have a way to do the derivative of the square root of x plus 3. All right, we can't do the chain rule. We can't do the product rule to it. We can't do the quotient rule to it. We can't do the power rule to it. We need another rule to do to it. And that's where that chain rule comes into play. So being able to split it apart is actually very important. One of the things that I typically end up looking at when we're doing this is I typically say, what's the piece that's annoying you? Make that your g of x. And in this case, the piece that's annoying us is the x plus 3. Because if it wasn't there, if it was just x, I could do it. So take the piece that's annoying you, make that your g of x, and then make the other part your f of x. So let's look at this one. Now, unlike the x plus 2 squared, which we could FOIL out if we wanted to, nobody in here is doing x minus 3 to the first or minus 1 to the 100th power and FOILing this out. It's just not going to happen. But we want to be able to find the derivative of it. So what's the piece that's annoying us? It's that x minus 3, x to the third minus 1. Yes, you would say the 100 because the 100 is really big. But if I had just given you y to the 100, you can do the derivative that easy, right? That's just 100 y to the 99. Done. So the 100 really isn't the annoying piece. It's the fact that there's something inside of it that I can't do. So when we're looking at this, just like we did there, I'm going to take and make my g of x the x to the third minus 1. And my f of x is x to the 100. That's splitting it apart. What's the derivative of g of x? What's the derivative of x to the third minus 1? Yeah, 3x squared. That's the derivative of the inside. Now, what's the derivative of x to the 100? We just did that, right? It's 100x to the 99. Correct? So it's going to be I don't want to put a bracket there. 100 x to the third minus 1 to the 99th power. So this part stays because that's that piece there. Well, yeah, we're gonna clean it up to get the final answer. The final answer would be 300 x squared x to the third minus 1 to the 99th power. Because 3 times 100, 300 x squared, and then that piece is the odd part. No. Okay.
Did you flip your variables? I'm looking at the equation.
Yeah.
So it says f prime times with parentheses.
Oh yeah, I did the g of x first.
Okay.
Yeah. Because it's multiplication, so it doesn't really matter.
Okay.
I have a tendency to always do it first because the first thing I do is typically the derivative of the inside piece. So yes, the one that they put, they have it opposite. So I put the g prime of x first. All right, let's do another one like that before I go on to, actually, you know what? Before I do the sine x1. Let's do this one next. Do this one next. All right, here's square root of x squared plus 1. So let's try this a little different. Let's make m x squared plus 1. And now my f of m is the square root of m. Everybody understand what I just did? I made m, I just made up another variable. I said m is the thing inside there. So I took this piece right here and I made it m. Because you can do that. I can technically replace anything I want. You're right. On purpose. It's in essence the same thing as saying g of x and f of x. Exact same thing. Right. F of x is that. f of m would be the square root of m. And if I replaced it with the x squared plus 1, it'd be f of x.
Like, you know how we have formulas of like x plus h plus that, which take for or the x plus h. Like, do they realize that they on this function?
I don't know, honestly. I don't remember. Like, composite functions isn't one of those things that's talked about very often, so I'm not sure when that was actually like that part was discovered. So my guess is that composite functions was done before this stuff, but it very well could have been the other way around. All right. What is the derivative of m? Derivative is just 2x. Bring the 2 down, subtract 1. The 1 disappears, correct? Okay. What's the derivative of f prime of m? Remember, that's m to the 1/2, right? So it's 1/2 m to the negative 1/2. Which is 1 over 2 square root of m. Yes or no? There's multiple ways to explain this. That's why that's why I'm trying to find the way that would click and make sure you understand. Do you understand how I found the two pieces? Okay. The 2x, 1/2. And then the m negative 1/2, that means it's going to go down the bottom because it's negative, and 1/2 is just the square root. Okay? All right. So we're good with finding those two things. The second part of this question is, do you understand this part?
Like the f of m, like I get x squared plus 1 like as the inside function, but I don't understand why it's just like the square root of m.
Because I'm literally just replacing the red part. So that goes there. I'm just replacing that. Because this way I don't have that extra function in there that's messing up where you're thinking about it. Okay? You could do this method for everything. What do you mean? Oh, I'm going to do another example. I'm going to do many more examples, actually. You want to give me a problem to try to do? No? Okay.
Yeah, I don't even know how it
No, I haven't done the final answer yet. Because I wanted f prime of x. So, f prime of x is 2x. Because that's the inside piece. Times 1 over 2 square root of x squared plus 1. I replaced back the m. So now it's all in terms of x. So, yes. So then putting it together, I would end up with just x over the square root of x squared plus 1. Because the 2's would cancel out. No. You can use parentheses. Brackets and parentheses are the same thing. It's just sometimes when I have parentheses, a bracket makes life a little bit easier. But no, that's just a preference on how I'm writing it. Let's do r of x equals all right. Write this one down. It makes life easier once you understand it. Huh? Does make life easier once you get it. Trust me. Huh? Fifth.
Professor, would you just divide the 5 by the 3 and get rid of the whole?
Yes. That's where it just.
Perfect. Thank you so much.
All right. I know this problem has multiple things that are going to annoy you. What's the first thing that we might want to deal with because it's really annoying? Yeah, we got a cubed root and we got a fifth power, right? Can we put that to do some kind of algebra so we don't have those? How do we take it away? What does your roots become? Yeah, 1/3. It's a fraction, right? It's a fractional exponent. So we can rewrite this problem just using algebra to 3x squared plus 4x minus 2 to the 5/3 power. Same thing I did on this one when I made it that m to the 1/2 power. Roots are just a fraction. Since this is a cubed root, it's to the 1/3. And since there's a 5 inside, that's where the 5/3 comes from. All right, so we've dealt with the cubed root piece. Just using some algebra to rewrite things. Okay. What is the piece inside? What's the part inside of the other function? Yeah. So we're going to take this, and you can use whatever letters you want. If I'll go back to the, so that would be the g of x is 3x squared plus 4x minus 2. What's the derivative of g of x? Six x plus 4. Okay. Quite often, power rule typically works for a lot of those. We're going to do some problems where you're going to have to do some other rules in there to make them a little more complicated, but quite often the power rule works for those. Oh yeah. I'm going to do enough easy ones first before I get to the more complicated ones. At least I'm hoping to. All right. What was the question? Yeah. Well, yeah. So basically, I'm going to use y just because I don't feel like writing multiple x's. But so if I had y to the 5/3, what's the derivative of that? Yes. 5/3 5/3 y to the 2/3, because it's subtract 1, which ends up being 2/3. All right, so r prime of x. We have 6x plus 4. We have 5/3. 3x squared plus 4x minus 2 to the 2/3. No, it's about as far as you can go. We can clean it up a little bit, kind of, but we can write it that way so it looks a little better. But in essence, those are exactly the same thing. So again, so it's the same concept, same problem that I had in my Calc 2 class last night. When you're writing your final answer, it's all about how you're using it after that point. Okay, so both those are fine. Depending on who you're talking to, the bottom part might make more sense to somebody who's not like understanding the fractional exponents and all that other stuff. So it all depends on where you're using your answer. Either one of those, I'd have taken it as accepted and give you full credit for. If you noticed in some of the other ones, like this one, I would have taken off a point because you didn't simplify it, because the twos could have canceled out. That would have been important. Or even like this one, that can easily go together. I would have rather the second answer, and I probably would have taken off a point for the first one. This one, it really doesn't simplify down anymore. You're not distributing the 5/3 because that's really not going to help you much. It's going to make it look worse, actually. So, like in this case, leaving it like either one of those would be totally mathematically fine. Okay. It ends up coming down to just purely preference. So, all right, let's do this one next instead of the sine one. Before I do the print function. I guess the table's not totally flat. That was weird. And it was like, I know, it's because it's wet, so it's slippery, but it's like the table must not be level. So it's like, okay, it's running away. All right. Now, this problem, yes. 3. There's no number there. It's just a 3 there. It's just the decimal point at the end.
Oh.
Yeah, it's a cube root.
So first thing we do, put this as like negative 1 half.
Almost negative 1/3. Because it's a cube root.
Oh, that's 3.
Oh,
So you will never, unless the mathematician's an idiot, see a 2. If it's square root, it'll be blank. It's implied. So if there's a number there, it's not a 2. Assume it's something else. Okay. So as this is written, we got a quotient, right? Do we really want to do the quotient product rule? No. We can rewrite this so that we don't have to worry about a quotient rule. Okay. If I brought it up top, it would become a negative exponent, correct? So we can change this, again, using our algebra to make this problem a little simpler to deal with, and write this as to the negative 1/3 power. So my g of x is x squared plus x plus 1. What's the derivative of that? 2x plus 1. Then I have y to the negative 1/3. What's my derivative of that? So f prime of x, 2x plus 1, negative 1/3, x squared plus x plus 1. So the negative 4/3 power. Can everybody see the screen okay? I know the colors are kind of like we can hit the lights, it'll be a little brighter if you guys want. I just don't know how dark it's going to be in here because it's not really light out. So no, this room, it's all or nothing. Yeah, it's one switch. I know some rooms normally I would shut off this set and just leave those lights on, but this room it's all or nothing. No, it's literally as bright as I can make it. This room has many issues. Well, yes, it would compare if I turned off the lights comparatively, but I can't make the actual screen any brighter. All right, this one you would want to clean up. You don't want the negative exponents. We've got a fraction in there, so this one you'd want to clean up. So the 2x minus or 2x plus 1 is going to be on top. And we have a negative. And then on the bottom will be 3 cubed root of x squared plus x plus 1 to the 4th power. You could have left it as x squared plus x plus 1 to the 4/3 power. That would have been fine as long as it's on the bottom.
Go further with any of this at any point, like after we get this.
If I asked you for the second derivative, you have to take the derivative of this. At some point.
Would that be easier to separate the numerator versus the denominator?
Well, at this point, you'd have had one of two options. You could have taken the original one we had here and done the product rule on it, or you could have done this and done the quotient rule on it. It's at that point, it's up to you. So. All right. Are you getting more comfortable splitting it up and looking at the actual, like the breakdown piece there? Okay. Let's look at a trig function. Because so far, everything I've dealt with, it's been simple polynomials. And we're not done with those. We're still going to do some more of those. Those do come up quite often. Well, they were like x squared plus x, those type of things. Not the actual chain rule is complicated. The first derivative piece was not. So we've got sine squared x. This is the same thing as saying sine x squared. Those mean the exact same thing. Okay? You can write the square in between it, or you can write it at the end. If you're going to write it at the end, you have to write parentheses around it, because that does not equal that. Okay? That's why you write the 2 next to the sign and not the x. So you know that the trig function is squared, not the x is squared. So if you're going to write it out like this, make sure you put parentheses around it. So now let's look at this in terms of the chain rule. So my inside piece is sine of x. What's the derivative of sine of x? Cosine x. What's the derivative of y squared? It'd be just 2y, right? Yeah, I know. Yeah. All right. So I've got cosine of x. Actually, I should have wrote an n prime. Cosine of x times 2 sine of x, which, if you finished your problem before, when you did this problem at the beginning of class, it was 2 sine x cosine x. You'd have gotten sine x plus times cosine x plus sine x times cosine x, which gives you 2 sine x cosine x. Or 2 cosine x sine x. It doesn't make a difference which order you put them. So this is easier than doing the product rule. Stay.
Find it. If we can remove each thing, like, oh,
And that's kind of like, that's why I did those problems at the beginning. Because if I did this, you wouldn't have gotten that they're literally the same thing. So it's like we use the rules that we already know. So you can get the answers, see the answer. Now we do it with a new rule. It comes out to be the exact same. And this always works. So there, if you look in the book, there's actually a long proof of it. I'm not going to go through the actual proof of the train rule because I don't think that's going to be helpful to you and probably confuse you more than help you. So the nice thing is it does just keep working. All right, let's do this one next.
why? In the last slide.
Yep.
I understand to do it, but why do you put the 2 in front of the sign if you're taking out? Never mind, you take the derivative of 2 and it goes in front of the sign and it's still sign.
Yes. Yeah, it's still, that function is still there. That's why it's still the y there. The y in this case was the sine x. It's still there. So that's why when I was doing the other ones, I made sure I wrote a color. It's like that's still black. That's still there. It doesn't disappear. So, all right. So here's what I want you to do. I want you to find me m prime of x and n prime of x. Okay? Find those two using the quotient rule. I mean, that's quotient rule, chain rule.
Oh, I see.
Yeah. Yes. Ignore the first. I took the problem and I split it up. I want you to find me m prime, the derivative of the first one piece and the derivative of the second piece. No, don't cover it up. I want to see what you're doing. You're fine. I want to see what you're doing. Okay, so that's correct. That's fine. Except that X is 2x plus 1. And I don't want to get two of this. If you choose option. That's just two. Because it's just the derivative of that.
Oh, so it's just two?
Yeah. So that, now do the derivative of that, but what's the derivative of that? Yeah. And that is just. Good, that's fine. Yeah. Best, you have a question? Okay. Do the derivative of the inside.
Oh, I never wrote it down.
Do the derivative of the 2x plus 1.
Thanks, you did. Okay, so I have the I split it up into 2x plus 1, and then then this one's x cubed minus x plus 1. So I'm kind of having fun with the variables here. So would I just make that and then the other thing be x to the 5 because that's the
And that'd be x to the 4. That's fine.
okay.
That's why if you notice when I'm doing it, I'm using a y because I don't. Although when you use the x's, you get really confused in your head. That's why I use this extra a different letter.
Thank you, Professor.
Yes. Yes. The only thing is, it's fine.
Oh.
Other than that, like that's the only change you're going to see me make on the board. But your answers are right. You're doing two separate problems. That's fine. Yeah. You don't have to. That's fine. So that one you multiply by that.
Oh, yeah. Because then it could look like.
Yeah.
four.
Right. I'm sorry. Yeah, you can do it like that before. It's fine. Let me do those. And that's right.
I got to the point where I was trying to find it.
Okay, hold on.
Yeah.
You're doing this. Yeah. That's not true. It's just. And Brent was, you're gonna find out one time by that.
So.
Professor?
Yeah.
Struggling a bit with this one. So I have the F1, so the 2, then the
Yeah.
G of X is X5, and then times G1 of X, which is 5X.
No, the X5 disappears. The X5 you don't need. It's F of G of X, which is this. And that X is the 2X plus 1.
You lost me there.
This is what happens when you use the same letter. All right, let's look at the M of it. Let's look at the F. So we have an original problem. I split it into two problems for you, which that confused some people, which is okay. The reason I split it into two problems for you is because we, in essence, are going to have to do the product rule for the original problem. Okay? You're doing the chain rule and then the product rule for this problem. Okay? I want to do the chain rule first. Because if you remember when we did the product rule, we had f of x, f prime of x, g of x, g prime of x, and then we did the product rule. That's in essence what I'm doing here. That's why we set up the product rule that way and had those four pieces. Because sometimes you're going to have to do a rule or a derivative for those pieces that are just not a simple thing. Like in this case, we have to do the chain rule. So we have m prime of x. I'm going to do the derivative of the inside piece. What's the derivative of 2x plus 1? That's 2. Okay? And maybe for the one, like, instead of trying to use different variables and stuff like that, colors can help. Okay? Because if you replace things with x's when there's already x's there, it makes it really, really confusing. So if you notice, that's why I was using y's, but sometimes that even can be confusing. So colors might help too. Now, we're going to look at the derivative of this piece here. I would bring down the 5. The 2x plus 1 stays to the 4th power. So then my final answer is 10, 2x plus 1 to the 4th power. And since most of you aren't old enough, back when I was a kid, we had the 10 clicky pens that had 10 colors on them. You can buy those on Amazon still, by the way. And you have 10 colors on your pen. It was the coolest thing in the world when I was in school. Like, everybody wanted them. Yeah. All right. So that first one, so the m prime of x is 10 times 2x plus 1 to the 4th power. All right. Now let's look at our n. So again, we're going to look at in the inside. What's the derivative of the x to the 3rd minus x plus 1? 3x squared minus 1. Period. That's it. We did not look outside. So that 4th does not exist in that piece that I'm doing right there. Now we're going to look at the big piece. So now I bring down my 4. Times x to the 3rd minus x plus 1 to the 3rd power. And in that case, you actually can leave that as is, or just put the 4 in front.
What was the point of doing all
What?
that?
This?
No, I didn't know. They're multiplying it, right?
Yes.
I get it. I get it.
All right. Now my garage camera is going to go off constantly. Oh no, they're replacing my garage door. I just need to mute the actual alert. Yes. It was to the 4th power. So I bring down the 4, subtract 1 from the exponent. Same concept here. Remember that I brought down the 5 and I did 5 minus 1 to get to 4. That's just the power rule. So if we look at it in terms of just the power rule, if it was m to the 6th, it'd be 6m to the 5th, correct?
Oh, yeah, I did.
All right. We're not done with this problem. This problem originally was a product rule. Okay? So we have to treat it like a product rule. We have now found the derivative of each of the pieces of the original function. Now I have to do my product rule. Okay? So yes, this is going to look long because it's long. So it's the derivative of the first. So I have 10, 2x plus 1 to the 4th times the second, x to the 3rd minus x plus 1 to the fourth plus the derivative of the second. So 4, 3x squared minus 1, x to the third minus x plus 1 to the third times the first. And that's my final answer. Yeah, because I didn't want a million parentheses. And the way I used the brackets here, it kind of separated out the derivative of the first times the second, and it was the 4 pieces. So, but yeah, I just didn't want to have a million parentheses.
Is that it?
That's it.
I was like,
No, so the only way, honestly, the only way to simplify this would be to FOIL everything out, which would be a nightmare. Yeah. So like you would leave it like this. This is as simplified as it's going to get. Yes. Yeah, because the product rule is the first thing plus the second thing. I just didn't have enough room to write it all in one line. So it's this plus this. That's why I indented it a little bit. All right. Other than it being long, are you starting to get the concept of the chain rule piece? Okay. I think colors would help you. Yeah, I really do think colors would help you. You're getting confused with your variables because you're using X for everything. Yeah, you literally just need 2 colors.
No, I have. Oh, thank you so much. I think I have one. The blue one somewhere.
Not like a lot.
Oh, crayon, that works too.
Oh, yeah, that's fine.
Crayon's perfect.
So yeah, I think the colors would help you. She's got a whole pile of them. She's got literally every color of the rainbow there.
Appreciate that.
Yeah, like, there's a lot of people that use colors to identify things, and I think it does actually really help organize your notes and stuff like that. All right, let's look at this one. Nope, to the 9th actually. If it was to the 0 part, it'd be easy. 1, we're done. Yes, the derivative is 0. We're good. Should try that one time. I like that problem. So my Calc 2 test, one of the questions on it, we went through and did this whole process, like the chain rule. It's more complicated. It's called trig substitution. And you go through and you can do it out. So the problem could be done that way. But it had one extra piece in it that allowed you to use a lot simpler method. So it's like I use a problem like that to test if the person actually is just rote memorization of the process or if they're actually looking at what they're doing. So that would be a perfect example of that. Put a 0 in there. Are you just going to actually just go through the process or are you going to catch, wait, that's 1, I'm done. Like those type of problems are good. Yes, they're tricky, but they're good because they actually are forcing you to think about what you're doing instead of just doing robotic doing a process that you've learned. So, all right, let's look at this one. So this one, do I have a, what do I say? Do I have multiple things that I'm multiplying together, like the last problem? No. So the last problem I had this times this. So that was the product rule on the outside. So I ended up having to do the chain rule first and then do the product rule. This one, it's one piece. So I have to do the chain rule. However, the part inside is a quotient. So I have to do the part inside as a quotient rule. Yes, just like we were doing before. So the first thing I'm going to do for this one is we're going to look at this piece there. So I'm going to change them to x's because, or I'll leave it as t's. I'll leave the t's. I hate using t's because my t's look like pluses, and I can never get the little curl on the bottom to look right. So find me the derivative of that. So you have to use the quotient rule for this one. Sure. No problem. So I've got 2c plus 1 minus. So that is your quotient rule. I can see how colors can help you. So the derivative of t minus 2 is 1. Derivative of 2t plus 1 is 2. So it's the derivative of the first. So it's 1 times the bottom, 2t plus 1, minus derivative of the bottom times the top. So 2 times 2t minus, or 2 minus, or t minus 2 over the bottom squared. So I end up getting 5 over 2t plus 1 squared. So that's the derivative of the inside.
split the two T on the bottom, the two problems, and cancel the terms out. Original instead of FOIL in the mouth,
Here?
like when you did the quotient.
Oh, here?
Yeah.
No, because I can't cancel that and that. I have subtraction. If it was in both of them, you could, but not in this case. Don't worry, I have another slide with all this on it, so it's not going away for your notes. All right, so what's the derivative of the whole thing now?
Five times two plus one squared.
So g prime of t. So 5 over 2t plus 1 squared. No. 9
Oh,
times 2t minus 2 over 2t plus 1 to the 8th. So remember, now we have to do the chain rule. So we found the derivative of the inside. That's 5 over 2t plus 1 squared. So that's the first piece. And then I multiplied by the derivative of the original function. Get that black. Put that original piece there. So I can clean this up a little bit. And that would be the final answer.
Would you still get the right answer? Let's say you just wanted to boil that out all the way to the 9th power and then took the derivative of that, whatever final.
It would give you the same answer as this, yeah. Uh-huh.
You're really stuck. You can't do that.
Well, yeah, until I give you 1 to the 100th power, like I did at the beginning. So yes, you can any kind of polynomial, you can always FOIL it out and get something that'll work. Okay, you can always go back to the power rule for a polynomial. Absolutely. How much work do you really want to put in to do that? Okay. So even to the 9th power, FOILing that out would take you a very long time. And even FOILing it all out, you still are gonna have to do the quotient rule. Okay, all you're eliminating doing is the chain rule, which honestly is designed to make it easier for you. If you remember, I told you one time, I'm not going to teach you tricks that only work sometimes. This is one of those tricks that always works that makes your life easier. So it literally is a shortcut to doing a lot of these more complicated problems.
Are you going to do it to where it's like 9x minus 1?
You can't, like to the exponents,
Yeah.
you can put exponent variables in the exponents, which we're going to look at. I'm not going to do like 9x minus 1, those type. Well, yes, but in a E standpoint. All right. So what's the derivative of e to the x? Right. And other than that, we haven't done anything really with natural logs and anything else. We can figure out all the derivatives for e to the x. We did those. But what happens if I give you 2 to the x? We don't have a way to do that yet. We only have a way to do e to the x. So we're now going to look at a way to be able to do things to other ones. So we'll be able to do 2 to the x, 3 to the x, 4 to the x, 5 to the x, anything like that. All right. So ln e to the x equals x. Does everybody agree with that statement? Okay. Ln and e cancel each other out, correct? Same thing over here. The E and the ln cancel each other out. So those two statements are true. As long as I do the same thing to both sides of the equation, does it change my problem? No. So if I raise both sides of the equation to some exponent, it's not going to change that problem. So if I raise both sides to p, I have EP ln of x equals x to the p. Everybody agree with that statement? Okay. Good. So based on what I just did there, if I said b to the x equals e x ln of b. So I took basically this. And, well, reverse the sides, but that became bx. So my b is where the x is. So that's b and b. And my x is where the p's are. Okay? Are we good with this? Okay. All right. Let's find the derivative of both sides. So d dx stands for derivative. That's just another way to write it. That's the Leibniz notation. So I'm going to do d dx of dx, and then the d dx of ex ln of b. So I did the derivative of both sides. We can't do this side. You have no way to do that side. This side, we have a chain rule. So let's look at the chain rule. We're going to take the derivative of that, which is what? What's the derivative of x ln of b? Just ln of b, because x ln of b is a constant in this situation, right? Remember what we did on the last class when I said if there's other variables, we're not dealing with them, we just treat them as constants? Ln of b is a constant in this case. So if it was 2x, the derivative would be 2. In this case, the derivative is just ln of b. Huh? No. What's the chain rule state? So my chain rule states that I have ln of b, right? Times the derivative of, what's the derivative of e to the whatever? It's just e to the x, right? So it's e to the x ln of b. Okay? What's that? On my screen somewhere, I have what that equals. That equals b to the x, right? Okay. So that can be replaced with just b to the x. So my derivative of b to the x is ln of b times b to the x. What's the derivative of e to the x? Looking at the rule I have above me. B is just e, right? In this situation. So I'd have ln of e times e to the x. What's ln of e? 1. So that's e to the x, which we've already claimed and stated that's true, right? So it's still true with this rule. What's the derivative of 2x? Ln of 2 times 2x. And that's it. Literally as far as you can go. So the derivative of any exponential function is just that times ln of whatever is there. All right. Do these. All right, what's the derivative of 5x? 5 to the x. Ln of 5 times 5 to the x. 7x. Simple, right? What about the last one? Which is almost 2x. But that's right. Why'd we do that? Because it's a chain rule. The other ones were just x. That's a function. What's the derivative of just x? 1. So it disappears. We don't have to worry about it. This one's 2 at x squared. The derivative of it's not 1. It doesn't disappear. So I have to put the 2x there. Times ln of 5, 5x squared. So the only thing that changes from f of prime to h prime is because of the x squared, I have a 2x out in front. Because that's the derivative of that piece there. All right. So every time we've done this so far, we've had one chain rule, right? Even the product rule, yes, we had to do the chain rule twice, but it was to two different functions. Does a chain only ever have one link? No. So the thing about the chain rule is, the nice thing about it, or the annoying thing, depending on how you want to look at it, is it can keep going. So let's look at this one. So when you look at this one, we have multiple chains. So let's look at that part first. So if g of x is cosine tan of x, and I want to find what g prime is, because that's in essence what I would want to do, well, I have another chain rule. We have to find the derivative of that part first. What's the derivative of tangent?
Secant squared.
Secant squared x. So the derivative of tangent x is secant squared x. What's the derivative of cosine x? Negative sine. So it's negative sine tangent x. Because that piece has got to stay inside. All right. Are we good to there? Not done. Because that's just that part. What's the derivative of sine? Cosine. So f prime of x is the whole piece there. So secant squared x times negative sine tangent x times cosine tan. Yeah. The only thing you might want to do is put the negative sign out in front, but other than that, it stays. Now you know why I typically don't like using multiple parentheses to use the brackets, because they're parentheses. So you can do multiple chain rules. All right. I'm going to add a practice for the channel in WebAssign. Because you don't have to do it. However, I truly believe most of you really need to practice some stuff on the chain rule. Okay. I didn't think so on the other ones. That's why I didn't create one for like the product rule, stuff like that. I think for the most part, you guys actually get the power rule, the product rule, and the quotient rule. I think for the most part, you guys get those. I do think the chain rule, you need a little practice on. Huh? Yes, it is. But it's one of those things that as you practice it, and it gets easier. It truly does get easier. It's just a lot of little moving parts that you got to kind of keep track of. So,
A little practice is an understatement for me.
well, there's 101 problems in this practice assignment for you. Huh?
Yeah, I have it. Oh,
Yeah, hold on. I need to stop this.
As the primary.
Yeah, I just want